Hello guys, in today's video. Today we will talk a bit about wires again. Today will be a small continuation about transmission lines. Here I have a small circuit based on Schmidt trigger IC, which makes very fast edges, and this is a thing that will finally show us the TDR show that the regular oscilloscope is capable of TDR measurements, and this is what I want to show you today with using this circuit. So my power supply is set to constant voltage 5 volts, as you can see there. Let's right now turn on the output, and this is what we see on the scope, the rising edge of the square wave. As you can see, that's how it looks like. Kind of simple. The frequency is 5.6, and here's a pretty big overshoot. And here we have a BNC jack on the output of the circuit. To this I will connect a small BNC to alligator clip cable, and as you can see, nothing changed. Right now I will get my transmission line. So here I have my big spool of wire, cut 5E wire, as a transmission line. And right now watch what happens when I connect some pairs to the signal. So let me connect orange one to the signal and the blue one to the ground, and that's what happens. As you can see, we have like two rising edges of our square wave. So right now, if I will add capacitance of my body on the other side, you can see that it very slightly decreases. If I will short the output, this is what we see. Basically, there is a small, very small negative, as you can see, point. We are just shorting this square wave, so that's not a good representation of shorted pairs. But if I will add another connection here, you can see that we have another bump. And then if I will add on the other side another connection, you can see more bumps on our square wave are appearing, because those are the reflections of the pulse. So the pulse goes through the wire, reflects from the back, and then it goes to our scope back again. So that's why we see this second rising pulse. So let's do cursor measurement. Let's do time, because we care about time right now. And let's put this cursor over here, somewhere here. And then let's put this cursor on the second moment when it starts to rise again. And this is our measurement, which is 168 nanoseconds. So right now, if I will find the material from the last episode about transmission lines, which I have here, in order to calculate properly the length of the wire, we need to divide the length by, it's a velocity. If we want to calculate the velocity, we need to divide the distance by time. So right now, if we want to know the distance, we need to grab our velocity, which we know in cut 5e wire, this is 0.19 times 10 to the 9th meters a second. We need to multiply it by 168, which I will do on my calculator. So we need to do 0.19 expanded 9 times 168 expanded minus 9, which equals 31 meters. And that's a good result. But what this result really shows us is not the true length, because we need to divide it by 2, because the pulse goes through the transmission line and it goes back to our scope. So we need to divide this by 2, and right now we have the true length of the wire, which is 15.96. And hello, you can see my face. So that's basically today's episode. This simple circuit is a Schmidt trigger square wave oscillator if you want to find it, and episode about my power supply will be in the future because I upgraded it, as you can see, from a small little boxy thing that was lying around my workbench to a finally different thing. And I can do constant current, constant voltage right now, so that's much more, much better. So that's the upgrade that I did from the last time, and see you in the next video.